So last time I gave you a formula for the, where did I put it? I gave you a formula for the effective potential energy of an orbit. The effective potential energy, and this is what lets us use the an energy diagram to understand orbits, is L squared, where L is the angular momentum of the orbiting body, divided by 2 mr squared, minus g big M little m over r. So this is the effective potential energy, and I drew a graph of what the potential energy looks like, so that way then you can more easily understand why this effective potential energy really does let us use an energy diagram. So this looks something like this. There we go. And so I can get rid of these now. So the question is and you know, if you had some energy total here, then it would tell you what the minimum and maximum distances were. Remember, this r is the distance from the source of the gravitational field, like the sun, to the planet, for example. This would tell us that this point is the aphelion or apoapsis. Apoapsis is just the general term for aphelion if it's not orbiting the sun, it's orbiting something else. And this distance here would be the periapsis or the perihelion. And so this is how you can figure out what's the maximum distance that an object can be from the object that's orbiting, what's the minimum distance. Now, we can learn more from this from a graph like this. So let's talk about orbit categorization. So we can actually start to categorize orbits based off of their total energy. So for example, when E total, you can name this this minimum value, we can name it R naught, just to give it a name. It's just the distance where the effective potential energy is minimum, and it differs, like it's not a fixed number, it depends on L, it depends on M, and all of that business. But so when E total equals the effective potential energy evaluated at R naught, meaning if your E total was down here, well, clearly that's a special case, and it would be helpful to understand what happens in that special case. What does that imply? It implies that the radial portion of the kinetic energy is always 0. And the reason for that is because the potential energy is equal to the total energy. So there just can't be any of the kinetic energy. And in this case, the kinetic energy the rate is the kinetic energy associated with the radial component of the velocity. And so what that means is that R of theta, or let me just write R, never changes. And that's just because the kinetic energy, the radial component of the kinetic energy, involves the time derivative of the distance r, dr dt. And so if this kinetic energy is 0, then dr dt is 0, meaning that r is just some constant. And so the question is what does it mean when r never changes? This is, i.e. the orbit is just the set of all points that are all the same distance from that point. This is a circle. So when the total energy is equal to the minimum potential energy, you get a circular orbit. Is there a capital or lowercase m? It's a lowercase m. I would have drawn it as a giant, but it's definitely lowercase. But you should have that from last time too. So we found one special case. When the total energy is equal to the minimum potential energy, you get a circular orbit. Further, what this implies is that all the kinetic energy that the object does have, because it does still have kinetic energy, just not radial kinetic energy, it's tangential. And that makes sense, because if an object is moving in a circle, it's the components of its velocity, or rather its velocity, is always parallel to the circle, right? So if it's traveling in a circle, the velocity is always parallel. It never has any component of the velocity that's moving towards the center of the circle. All right, there's another type of, and there's another type of orbit that we can talk about. When the E total is equal to 0, what does that imply? Well, it implies that so that means that the E total would be here. It implies that the object could get infinitely far away. In particular, it implies that the kinetic energy, the radial component of the kinetic energy is 0 when r is infinitely far away. Sorry, when r is infinitely large, i.e. when the object is infinitely far away from the object it's orbiting. And so this is, in a sense, what it means to escape in orbit, or an orbit. So where would so the kinetic energy is the difference, or the radial component of the kinetic energy is basically this distance here. It's the distance from the energy to the potential energy graph. So this would be this distance would be the kinetic energy if the total energy is this much. And so if the kinetic energy is 0, then when r is really, really big, the radial component of the kinetic energy gets smaller and smaller and smaller, right? Because the total energy is the x-axis. So we can see that the kinetic energy goes to 0 when the distance gets infinitely far away, but it's still always positive because this component is always slightly lower than the x-axis. So it always will have a very, very minimal amount of kinetic energy as it gets further and further away. And so the point is it can keep going. It'll slow down, but it'll always keep going until it's infinitely far away, at which point it stops. And so this would be called, this is what it means to escape in orbit, that you can get infinitely far away from the object without turning around and falling back. And this particular orbit has a name. So let me just write that down really quick. This type of orbit has a name, and it's called a parabolic trajectory. It means when r is approaching infinity. And so the reason it's called a parabolic trajectory is because if you were to draw this, like if this is the orbiting body, and then you have your object starting out here, and then it's going around, it actually forms a parabola. And so like that is the shape of the trajectory. It forms a parabola with the source of the gravitational force at the focus of the parabola. What this means is it means as the distance r from the gravitating body to the source of the gravity goes to infinity. This is in a limit. This is a limit. And you could figure out that it is indeed a parabolic, like that it has this parabola shape. But it takes a little bit of work. So maybe just trust me on that. And then there's the last type. So we talked about when the orbit has minimal energy. No, actually that's using this last type, which we'll get to. So if you have minimal energy, you have a circular orbit. If you have between minimal energy and 0 energy, then you have a typical elliptical orbit. There's nothing really special there. It's just an ellipse. If you have 0 energy, you have a parabolic trajectory. And if you have total energy that's greater than 0, well, what does that imply? That implies that the kinetic energy is greater than 0, even when r approaches infinity. So it'll never slow down to 0. The kinetic energy won't approach 0 even as you get infinitely far away. You'll just be coasting off forever with some speed. And so this is just like a more extreme escape trajectory. And it has a name. This is called a hyperbolic trajectory. These are just ways of categorizing trajectories. And this is the type of trajectory that gravitational assists use. And the reason why gravitational assists use this type of trajectory is because they don't want to be trapped by the thing that they were, or by the planet, for example, because that means that the planet would forever slow them down. If they have a hyperbolic trajectory, then they keep some of their speed even as they slingshot around the planet. And so this looks a lot like the parabolic trajectory, but it's like more extreme. Yeah, so in that case, the E total would be above the x-axis, and so the kinetic energy would just be the difference. Like if the E total was, say, here, the kinetic energy would just be this distance. You could calculate that difference there, and that would give you the radial kinetic energy. Oh boy. There we go. Put it back. Right, so these are just like I guess there's 4 categorizations because I left out the elliptical orbit, but that's just the standard one where the energy is somewhere between the minimum and 0. Like the circular orbit is just a special case of an elliptical orbit. Okay, so they're not. I mean, okay, it depends on how you define orbit, right? They're orbits in the sense that they are a path that's influenced by gravity. But they're not in orbit in the sense that they are orbiting. They're not periodic. So call it what you will. That's why I use the term trajectory here. But you can still talk about the energy associated with an orbit that has greater than 0 energy for that reason. So we're kind of going to change gears here. It's related to this business of parabolic trajectories. But now we actually can apply some or do some mathematics here. So let's talk about escape velocity just for a minute. This is going to be a quick bit. So when we talked about the parabolic trajectory, I used this word escaping an orbit. So or maybe I should have used escaping a gravitational field or something like that, or a gravitational influence. But the point is if you're moving fast enough so that you can get infinitely far away, and only when you're infinitely far away does your speed drop to 0. That's what it means to have escaped that object's gravitational influence, right? You've gotten infinitely far away from it. You didn't have excess energy. You had just enough to get infinitely far away from it. And so when we talk about the escape velocity of a gravitational body, what we're really saying is how much energy how much velocity do you need to have when you start at some distance to get infinitely far away without having any left over that was extra. So what we really mean is...
Wait, could you repeat that again? I want to type that down.
I'm going to write it down. So, so we define escape velocity to be the velocity. So this is the outward pointing velocity, by the way. The velocity needed, actually, okay, let me rephrase. It doesn't actually have to be outward pointing. This is just the speed needed. So that the total energy of the system, the gravitational potential energy plus the kinetic energy, is equal to 0, starting at distance capital R, let's say. So the point is how much, if you are initially a distance capital R away from the object that you're trying to escape, and this would be from the center of the object. So if you're on the surface of the Earth has a radius of like 6,400 kilometers. So you would plug in R as 6,400 kilometers. Then the escape velocity at that distance, 6,400 kilometers, would be the amount of speed you need to go, or the amount of speed you need to have in whichever direction, so that you can get infinitely far away from the Earth without having any leftover speed. So we can actually just solve this. We want the total energy to be 0. And so we have a formula for that. This is 1/2 times m v rad squared. This is the radial component of the kinetic energy plus the effective potential energy, and we plug in the value of R. So this will be, we could solve it this way, but this would only tell us that if you have a radial speed of such and such an amount, then you will have, then your escape velocity can be such and such an amount. But we don't want it to just involve radial speed, because you can escape a gravitational system by going in any direction. So instead, let's rewrite this using just the original potential energy for gravity. And so what we get, remember how we got the effective potential energy? This is just the full velocity now, and it's just plus the gravitational potential energy, not the effective gravitational potential energy. Remember that in this case, U of R would be negative GMM divided by R. I mean, it's just a capital R. I'm just using it instead of lowercase r because we usually use lowercase r for a variable. This is, like, in this case, capital R is a constant. And so we can just solve this equation. We can solve for the speed needed. It implies that the escape velocity, maybe I should have substituted in, or substitute escape here. The escape velocity as a function of the distance that you are from the object, square root, that's a 2, not a G, 2G capital M divided by capital R. So if you start off 6,400 kilometers away from the center of the Earth, and you plug in the mass of the Earth, multiply by G, multiply by 2, and then take the square root, that will give you a velocity. You can check the units yourself. And that says that if you go in any direction, presumably not into the Earth, because then you'd hit ground, but if the ground wasn't there, then it would be fine. If you go in any direction with that speed, eventually you will leave the Earth's orbit. That will give you enough speed that by the time you were infinitely far away from the Earth, you would have 0 speed left over, because the Earth is always constantly pulling on you. So something which would break the velocity into radial and translational just by using omega equals, no, I wouldn't. Yeah, I guess you could. It doesn't seem like a particularly useful thing to do, though. So just as a quick remark, so from this formula, if you want to escape the gravitational influence of some object, it doesn't depend on the mass of the thing that's doing the escaping, right? Let's say you're in a rocket ship and you want to figure out how fast do you have to be going to escape Earth's influence. Let's say you're in space or something. Well, it doesn't matter how much your rocket ship weighs. That doesn't show up in this formula. It only matters the mass of the object and how the mass of the thing that's pulling on you, and the size and the distance that you are from that thing. So, which is kind of strange, because you'd think that like heavier things would need more speed to escape. But it's just not the case. Now, there is one cool caveat that we can, or one cool consequence that we can learn from this formula, and that's that, well, we know that light has a speed, right? It has a fixed speed, in fact. But also, if you guys have, dug around on the internet at all, you also might know that it has no mass. Fortunately for us, by the way, this speed, often abbreviated by lowercase c, and it's equal to 3 times 10 to the 8 meters per second. Almost. It's off by like a few thousandths of a percent, but it's basically that. So light has a speed, so you might expect that you could use this escape velocity formula, because it doesn't matter that it doesn't have a mass because no mass shows up in here. But then you might ask, well, is light really affected by gravity? So it turns out that light is affected by gravity. Understanding that requires a little bit more physics than you guys have. It requires general relativity. But as long as you trust that light is indeed affected by gravity, and by the way, you can check this by seeing that the light from behind the sun can be bent around the sun so that you can see it. Like that's a thing that was observed in 1917, I want to say. And so you could figure out how heavy or how much mass would need to be concentrated into a region of how big a size so that even light could not escape from that area, from that region. i.e., what is the size of an object of mass m if light can't escape from it? Now, you guys all know that, or hopefully you know, that light is the fastest thing in the universe. Nothing can go faster than light. So if light couldn't escape it, then nothing could, and this would be a very strange phenomenon. And so in fact, what we can do is we can just solve this equation and solve for the distance for the size of the object r, imagine like the Earth has like the radius of the object, so it'd be like the radius of the thing that light can't escape from. We can just solve. C should be equal to square root 2gm, so it has some mass m, and it has some radius r. So we can solve this equation, and we find that the radius, and I'm going to put a subscript s here for a minute, and I'll tell you why in a minute, the radius of this object is equal to 2gm over c squared. This formula, or this value of the radius, if you plug in a value m and you plug in g and c, you get a number. That number is called the Schwarzschild radius. I always need to check how to spell this. It's a very German name. He was a fellow that lived in the late 1800s, early 1900s. He worked with Einstein, actually. Unfortunately, he actually derived this result for the first time, or he derived where this result gets its name from, why his name is on this result anyway, in the trenches during World War I. And he actually died before this work was published, but he did send it off to Einstein, and I believe Einstein published it posthumously in his name. So a little bit of physics history for you. Right, so yeah, he was drafted. He didn't want to be in the war. So the point is if you take like a flashlight, and let's say that you are a distance one half of this whatever. Let me start over. Let's say you have a whole bunch of mass, like concentrated in a really small area, so you can be whatever distance you want from it. Say it has mass capital M. Let's say you go a distance r sub s away from that mass. Maybe that's 5 meters, maybe it's 1,000 kilometers, whatever it is. You go half that distance. And then you turn on a flashlight. Well, at least from a classical perspective, that light would go out, and then it would stop, and then come back to you. Because the light can't escape. Like, it's not going fast enough to escape the gravitational pull. Now, that's a classical perspective of what happens. In fact, what actually happens is slightly different. I can talk about that after lecture if you're interested. But but from a classical perspective, that's what we would expect to happen, that even light is not moving fast enough to escape. So let's just work out an example. So for Earth, how close to the center does the flashlight need to be to not be able to escape? The Earth has some amount of mass we can figure out, and then so we can plug that mass in for this r sub s. So we can just calculate it. It turns out that the Schwarzschild radius of something with the mass of Earth, it's a function of mass after all, is about 8.8 millimeters. Very small. So, however, this doesn't mean that you just have to drill down deep enough into the core of the Earth to put a flashlight there, and then that flashlight won't be able to send light up. Because most of the mass of the Earth is outside of that 8.8 millimeter radius. Right, so it's not like all of the gravity would be pulling it towards the center. And so what we really need to consider is that if you want this Schwarzschild radius to apply, you have to have all of the mass be inside a region that's smaller than the Schwarzschild radius. So what it boils down to is if you took all of the mass of the Earth and you squished it down into something the size of, say, a pea, which is less than 8.8 millimeters across, and then took a flashlight and shined a light out from its surface, then that light would not be able to escape because all of the mass of the Earth would be pulling on it back towards the center. Whereas if you were to do this from the center, from like the real Earth, most of the mass is outside pulling it out. And so that mass just doesn't affect the light at all. And so the bottom line is, and let me just write this out. If we squished all of Earth's mass into a region of radius, and technically it would have to be less than 8.8 millimeters. That looks like a C. Then light could not escape from its surface, and so Earth would become what is known a black hole. And that's what a black hole is. A black hole is it is a location in the universe, or it is an object in the universe that has so much mass compacted into such a small area that even light cannot escape from a certain distance away from it. And because light is the fastest thing that can exist in the universe, nothing can escape from a black hole. And the reason why it's called a black hole is because the way that we see things is light bounces off of a thing, and then it bounces back to our eye. But if light were to try to bounce off of a black hole, it would go towards the black hole, hit it, and then it would try to come back, but it couldn't, because light can't escape from it. And so you just can't see anything, hence black hole. Right. So now we're going to change gears completely. We'll come back to what we're about to talk about is kind of a long detour that will help us, or that will help you guys answer problem 6 on the homework. So we're going to talk about simple harmonic motion. Stop it. My tablet keeps thinking that my hand is my pen, or is my finger. Sorry, not problem 6. I think it's problem 4B or 4C and D. Yeah, it's sorry. Questions 3, C, and D. You guys don't really have the stuff for it yet. So let's start with simple harmonic motion. We'll get there. So we want to consider a spring with mass m, attached and stretched and released. And we're going to ignore friction, just because we're trying to understand the mathematics behind some of these forces. And if we imagine that friction's a thing, it just makes everything messy. So the picture is you have a spring attached to a wall, stretched out. And maybe the equilibrium distance for the spring is like here or something, call it x equal. And so maybe it's stretched a distance a. This block has mass m. So initially, and this is when I wish that I had animations, before you release it, the kinetic energy is 0. And the potential energy, well, we know the potential energy of a spring system, right? It's 1/2 times k times the displacement from equilibrium squared. So I'll just put a k here to indicate that it has spring constant k. So the kinetic energy is 1/2 times k. Now the distance that the mass is from the equilibrium is just a. So it's a squared. Okay, so that's the kinetic energy. After you release it, after a little bit of time, it's being, well, once you release it, it's being pulled to the left. And so eventually, after, maybe a second, maybe 5 seconds, whatever, it is pulled back to equilibrium. I don't even need to write that out. And so maybe then it's only compressed this much. It's at equilibrium. But the important point is that it was pulled to the left, but the amount that it was pulled by decreases. Remember that the force on a spring, the elastic force, is proportional to the distance that it's stretched away from equilibrium. So initially it has some really large force when it's here, but then the amount of force decreases until it gets to 0 in the middle. But it's been speeding up this whole time. So it keeps going. It has some velocity once it's at the middle of the thing, and it just keeps going. So I'm just going to put a little, stop it. I'm just going to put a little V here to indicate that the mass is still going. And so here, the potential energy is 0 because the displacement from equilibrium is 0. And the kinetic energy, well, energy is conserved, right? So it's still 1/2 kA squared. And then you could use that actually to solve for the speed of the object, because you know that kinetic energy should also be 1/2 mv squared. So you can solve for v in terms of a. And it keeps going, right? It keeps going because there's no force to stop it in the middle. However, once it passes the middle, it'll start slowing down because now the force is trying to pull it back to the middle, even though its velocity is moving away from the middle. So it'll slow it down. It'll make its acceleration be in the opposite direction of its motion until eventually it stops because the spring gets so compressed it wants to push it back. So then the picture would look something like this. Very compressed. The equilibrium position is still in the same place, and now it's stopped. V equals 0. And so again, because energy is conserved, when the kinetic energy is 0, that means that the potential energy has to be 1/2 kA squared. And what that means is that the location where it stops is also a distance a from its equilibrium position. And by the way, I know I've done this sort of thing before, but I'm just going over it again because it's been a while and because it's a good precursor to what we're going to talk about. And then it just continues. So then it goes back to equilibrium, this time moving to the left. And then the kinetic energy is again 1/2 kA squared, and the potential energy is 0. And then it goes back to where it started. Stretched out quite a bit. It is stretched out by amount A. It's stopped at this place. And then the kinetic energy is 0 because it's stopped, and the potential energy is back to where it started. So this is all just, this should all be familiar to you guys. All it was is it's just what happens, how a spring oscillates. But the important point is that this is like a cycle. It started off at some place with some velocity. It goes through a process, and then it ends back up after a certain amount of time. It ends back up at the same place with the same velocity. So this simple spring mass system is an example of oscillatory motion. It oscillates, meaning that it repeats itself, but it doesn't just stay in the same place forever. Like, for example, if I just put this pen on my hand, it's staying in the same place after a certain amount of time, but it's not doing something and then repeating. So oscillatory motion is motion that both repeats itself but also changes, i.e. like the state of the system is changing over time, but every certain amount of time it repeats itself. So the question is what was it about the elastic force, because keep in mind the only force that was present here was the elastic force, that made it so that it undergoes oscillatory motion? So we can actually answer that question. First, we needed that the spring force is conservative, because one of the ways that we knew that it returned back to the same position that it started at was that when its kinetic energy was 0, that it had the same potential energy that it started with, because its kinetic energy or its total energy never changed. But if the force wasn't conservative, then the total energy would change over time, and because energy wouldn't be conserved, at least not mechanical energy, and so you wouldn't be able to end up back where you started. So we needed that the spring force is conservative, and indeed that's true. We know that that's the case. However, we needed just a little bit more than that. We also need that the spring force is a two-way one-dimensional force, or one-dimensional restoring force. So the important things here, that it's two-way, it means it pushes and pulls. You can imagine a one-way one-dimensional restoring force that's like a spring that doesn't compress. So like it's at equilibrium. It will pull back on you if you try to stretch it, but it won't push back on you if you try to compress it. So that wouldn't work, because then it would just it would pull it towards the center, and then it would just go and hit the wall. That it needs to be two-way. It needs to pull and push. And the fact that it's one dimension means that the the direction of the force is the same, or it's in a parallel direction. In fact, it's in the opposite direction as the displacement. I.e., if you displace in one direction, the force will be in that same will be along that same axis. That's what it means to be a one-dimensional restoring force. And then restoring force just means that it always the force applied is in the opposite direction of that displacement. So we need both these features in order to get this sort of oscillatory force or oscillatory motion. Now, it didn't have to be the case that it had to be like kx, or that the force is negative kx. It could have been negative kx cubed for all we know. You would just as well get a two-way one-dimensional restoring force that's conservative, and you would still get oscillatory motion. It would just be more complicated. Now, there are other forces that cause oscillatory motion, like the one I just mentioned, but they're like real-world forces. You guys maybe remember the Leonard-Jones potential. I think I talked about that when we were first talking about energy diagrams. That's the force between two molecules that binds molecules together and binds atoms together. And that produces oscillatory motion, because you have molecules that like oscillate back and forth, right? That's oscillatory motion. However, the elastic force is like the simplest, and it's the most it's like the most fundamental force that causes, or it's the simplest force that causes oscillatory motion. So we're going to study it because it's very straightforward and it allows us to understand oscillatory motion. So in fact, oscillatory motion that's caused by the elastic force has a name, or has a unique name. It's called simple harmonic motion. And it gets a name because it's a special type of oscillatory motion. And it's a very straightforward and very well understood type of oscillatory motion. So a system that oscillates this way these are just definitions or jargon that you should know. Let me write, please. Please. Oh. Okay, I guess OneNote just crashed. All right. There we go. Right, so a system that oscillates this way, that oscillates that undergoes simple harmonic motion, has that type of system also has a name, and it is called a simple harmonic oscillator. Physicists are not the most creative people when it comes to naming things. However, giving it a name like this gives us a nice way to abbreviate it, called an SHO. So I'll be using this abbreviation a lot. It just means that it describes any system that can be characterized by motion that oscillates in this regard, or where something oscillates in this regard. Oftentimes, in fact, you can break up a system, or you can break up a model of a system into two separate models. There's the part that moves in one way, and then there's the part that moves like a simple harmonic oscillator. And then you can analyze the simple harmonic oscillator part separately from the other part. Like imagine that this whole system, like this wall and the mass, were moving vertically. You could break up the system into a point mass that's moving vertically, and then a simple harmonic oscillator that's not moving at all, or that's not moving vertically at all. And then you just combine those two systems. So it's a useful kind of atom for understanding systems, because if you can break up a system into a simple harmonic oscillator plus other less complex things, then you can recombine them and understand the whole system. Right. So we're going to actually analyze the motion of a simple harmonic oscillator explicitly. We are running short on time. I'm going to go a little bit over today and a little bit over on Monday. Sorry, but we have stuff to cover, and I want to make sure that you guys can do the homework. So we're going to do analysis of an SHO. Okay, so let's start with the picture that we had above. Starts out being stretched past its equilibrium point. We're going to call that equilibrium point x equals 0. We're just going to use a coordinate system where x equals 0 is there. And then we're going to have, the object will oscillate left and right. We'll call when it's to the right of equilibrium positive. We'll call when it's to the left of equilibrium negative. I'm just establishing a coordinate system here so we can actually do some analysis. Now, initially, the force on the spring or the force on the mass is just the spring force to the left. But if it was on the other side, it would be to the right. It doesn't matter. But the point is that because this is a one-dimensional system, we don't have to use vectors. We can just use plus and minus like we have. So in this case, the net force at all instants in time on the object is negative k times its position, x. And that changes with time, right? X changes with time, but you can check. So initially, when x is positive, i.e. the object is to the right, it is a completely new topic, but we're going to link back to gravity via the homework. So I need to introduce this stuff so that way you guys can answer the homework question about gravity in questions 3C and 3D. But yes, this is a separate topic. It's chapter 8 in the textbook. I did say that we're moving on to something completely different. Right, so when the object is to the right, x is positive. And so you can check that when x is positive, you would get a net force that's negative. And a negative net force means that the force points to the left, which indeed it does when the object is on the right. So Newton's second law would say that negative kx, where x is the coordinate position of the mass, should be equal to the mass times the acceleration of that object. Now, again, that acceleration is also not constant. It's changing with time because the acceleration changes with its position. Now, here's a reminder. The acceleration of an object is just the second time derivative of its position, right? That's just a true fact. If you take two derivatives of its position as a function of time, you get the acceleration. And in the past, the only acceleration we've really dealt with has been acceleration that's at least constant in magnitude. But now the acceleration is not constant in magnitude and in fact must oscillate because the position oscillates. So what we're left with after we substitute this back in is we're left with that we get negative kx. And by the way, all of these are functions of time now. X and a are both functions of time. This should be equal to m times d squared x dt squared. It's equal to m times the second derivative of position. And so we can rearrange this equation, do a little bit of algebra, and we end up with the equation d squared x dt squared plus k divided by m times x equals 0. And so this equation here looks like a scary equation. It's a differential equation. This is the equation of motion, or EOM. For in SHO for a simple harmonic oscillator. So every simple harmonic oscillator will have an equation of motion that looks like this. Maybe the numbers are different. Maybe instead of having k and m there, maybe it's different variables. And maybe instead of being x, maybe it's z. But any time where you have the second derivative of something plus a number times that something equals 0, that means it's a simple harmonic oscillator. Always. This is in fact how we define a simple harmonic oscillator, something that obeys an equation that looks like this. So now the question is, how do we actually figure out what x is? Like, this is a differential equation. You guys probably haven't taken differential equations. Fortunately, this is a really easy one that we can solve just by guessing. And we want to know how to solve this. If we can figure out x of t that solves or that satisfies this equation, meaning if you plug in x and then take two derivatives of x and plug that in, and then you get that the equation still holds, then we know what the position vector of x has to be, sorry, the position of x, or the value of x has to be as a function of time for all possible times. So people say that physics is about predicting the future, and this is the sense that they mean. They mean that you can take an equation, a simple one like this, that describes an oscillating system. If you can solve that equation, and by solve I mean find x that satisfies this equation, that makes this equation true, the function x of t, then some random person could give me a time t, and I could tell them exactly where that mass would be at that time. That's what we mean to predict the future with physics, because that's literally what you're doing. The question is how do you actually find that x? How do you find an x that does this? So let's instead look at a simpler problem and see if we can solve that one. Instead of having variables k and m, let's just look at d squared x dt squared plus x equals 0. It's clearly simpler. So let's just guess and see if we can come up with any. Well, polynomials won't work. Because if you take the derivative of a polynomial, let's say x is like t cubed plus t minus 5. It doesn't matter what the polynomial is. When you take two derivatives of that polynomial, you'll get a polynomial with a different power as its highest power, right? Like that x cubed will become a 6x, will become a 6x. So there's no way that you could cancel off the x cubed here, the x cubed in the term without the derivative. So polynomials are no good. They don't work. What about rational functions? This is things like x squared divided by 3x plus 2. Well, rational functions also won't work for the same reason that polynomials won't work. Basically, that the numerator always has a decreasing power. What about exponentials? So somebody suggested, Noah suggested exponentials, and that's close. Two time derivatives of e to the t, for example, that's just equal to e to the t. But that's not quite there because we need them to add together to be 0. So this is not equal to negative e to the t, which means it's not quite there. However, there is something closely related to exponentials that we also know whose second derivative is the negative of itself. That's trig functions. Trig functions work because if you take, say, two time derivatives of the sine of t, you get one time derivative is cosine of t, then the derivative of cosine is negative sine. So you end up with negative sine of t, and that's exactly what we need, because if you add two time derivatives of sine of t to sine of t, then you get 0, because they would cancel out. One is the negative of the other. And so it turns out that solutions to equations like this, and indeed to equations like this one, they are trigonometric functions. In particular, they're sines and cosines. So if we dress up the sine function enough, we can actually solve the above equation.
Wait, that was a second derivative being added to like the original x, right?
Yes. So negative sine of t plus sine of t equals 0, right? So that's the second derivative of sine of t added to no derivatives of sine of t, giving you 0. So that solves this problem. That solves that equation. So when I say dress up the sign, what I really mean is just come up with an Ansatz or a guess. Ansatz is German for guess, I think. It's just a word that's used in physics a lot. We'll be done shortly, by the way. And so we're just going to guess. Let's say that x of t has the form a, where a is just some number, times the sine of omega, which is also just some number, times t, plus the Greek letter phi. It's not 0, that's a Greek letter phi. So here, a, omega, and phi are constants to be determined. So this is our guess, and now we're going to see if our guess is good, we should be able to plug this thing in to our original equation. Yes, that is why. We're going to plug this in to our original equation and figure out what those constants need to be so that this solution, this guess, works for the equation that we're interested in. So let's check. dx dt would be, well, so you have to use the chain rule here. It's a omega cosine of omega t plus phi. And so the second time derivative is negative a omega squared, I was about to write cosine, sine omega t plus phi. By the way, another reason why we're talking about this now is because oscillations are like the first half of 9b, and so you definitely need to know about this stuff. So now let's plug this in and check. So now we actually need to check that our Ansatz, or that our guess, our Ansatz, works. So plugging in, we now know what the second time derivative is. So let's plug that in there. So we have minus a omega squared sine of omega t plus phi. Then we want to plug in plus k divided by m times the original function, a sine omega t plus phi. And that's all supposed to be equal to 0. And now we can try to solve for some of these things. Well, a can cancel out. In fact, all of the sine can cancel out as well. So what we're left with is that k divided by m, or negative omega squared, plus k divided by m should equal 0. Or, put a different way, omega, one of the constants that we just plugged in, we didn't know what it was, is k over m. And so our guess works so long as whenever we say omega, what we mean is k is the square root of k over m. However, do note that the constants a and phi, they can be anything. At least they're not constrained by the equation of motion. In fact, these constants are fixed by things called initial conditions, i.e., those constants in our guess would be determined by things like how fast was it originally moving, how far was it, how far away from equilibrium did it start out at. That constant, or those constants a and phi, hold information about those particular things. Now, I think we'll stop there for today. Didn't get as far as I would have liked to. I'll have to go a little bit longer on Monday, but as well. But we'll stop there for today by, I guess, just basking in how we started off with just a force diagram and a coordinate system, and we ended up, after doing some analysis, with a function that if you just plug in the values of t, it spits out where the object is. Now, we haven't actually finished. I haven't told you how to figure out what phi is. I haven't told you how to figure out what a is, because that takes a little bit of work, but maybe you could imagine that you could figure it out by just plugging in those initial conditions for x and v. Remember, v is the time derivative of x. Say x of 0 equals a number, and then you'd plug in t of 0 and see what that gives you, and then you'd get v of 0 equals a number, and then you'd plug that into whatever that should be, and then you could solve for a and phi, because it wouldn't cancel out. Anyway, I'm going to stop the